A warm welcome to electronic circuits. In this video we will learn how to analyze CE amplifier using hybrid pi equivalent circuit. So when we do the analysis of amplifiers, we will do AC analysis and DC analysis, and then we will apply superposition principle to add both the AC and DC analysis to get the terminal voltages and currents of the amplifiers. So when we do DC analysis, we will consider capacitor are considered to be open circuit. Why? Because the reactance of the capacitor is 1 by 2 pi Fc. In DC, F is frequency is 0. So when F becomes 0, reactance becomes infinity. Infinity is nothing but open circuit. The second procedure is we will contain the circuit is purely consisting of DC and AC is made equal to 0. When DC is considered, the equivalent doesn't contain any AC, so the circuit is called AC equivalent circuit. And while when the circuit is biased with DC voltages, we are doing what is called as biasing, and we are going to fix the Q point. And the final stages, we will determine what is the collector to emitter voltage, base current and collector current. So this is what we do in DC analysis, and it is also called large signal analysis. Why? Because the voltages and currents involved in this analysis will be large, so it is called as large signal analysis. When you go to AC analysis, the capacitance is considered to be if you take XC, it becomes 1 by 2 pi Fc. When frequency is sufficiently large, XC becomes small, so it is considered to be short circuit. And circuit will contain only AC and it doesn't have any DC, so it is called this condition is called where DC is made equal to 0. Circuit will contain only AC and it is called AC equivalent circuit. When you take the next step, you have to replace the transistor by its equivalent, and we are going to determine input impedance, output impedance and amplifier gain. This is what is the end outcome of AC analysis or small signal analysis. So in the previous slide we have seen we are going to use model. We are going to replace transistor by its model. And what is a model? Model is a combination of circuit element properly chosen that best approximate the actual behavior of the semiconductor device under specific operating conditions. So this specific operating condition says that the transistor is going to be operated in active region, because we are going to bias bipolar junction transistor in active region. So this is an NPN transistor. Between base and emitter we have a resistor R pi, which is called as a diffusion resistance. Between collector and emitter we have a current source GM pi. We have R naught, which is going to be simulated as yearly effect. Yearly effect. This V pi is nothing but voltage across R pi. So voltage across R pi is IB into R pi. So when I write GM V pi, it is GM R pi into IB. So this GM R pi is nothing but beta times IP, which is nothing but this is equivalent to beta. So I could replace this GM V pi by a beta into IB. So both are equivalent, one are the same. When you take PNP transistors, emitter is higher potential than collector. That is why emitter terminal will be on the top and collector will be on the bottom. So we have same model, but the current is reversed. GM into V pi into GM into V pi will be the current source, and R naught is modeled due to the presence of yearly effect, and GM V pi is equal to beta times IB. So this is the equivalent when you consider PNP transistor. So next come the common emitter amplifier, where when you consider this, the emitter terminal is present at ground. Emitter is present at ground, which is common for both input and output. So it is the common terminal. So when you take output, it is taken across collector and emitter. When you apply input, it is applied across base with respect to emitter. That's why it is called as a common emitter amplifier. And when we do the AC analysis, DC should be made equal to 0. DC has been made equal to 0. So R1 and R2 appear to be in parallel, and this Vs and Rs is nothing but Thevenin's equivalent of the input source. This CC is considered to be coupling capacitor, which allows only AC, which is going to couple AC, and it is not going to allow DC. So it is going to allow AC, couple AC and block DC. So the signal is given to the base of the transistor. Both R1 and R2 will appear to be in parallel. Why? Because the R1 other end has been grounded. When we consider AC analysis, DC should be made equal to 0. So it appears to be in parallel. So R1 and R2 is parallel. After that, we have base and emitter. Between base and emitter, we have R pi, which is nothing but the diffusion resistance. So that will come. After that, between collector and emitter, we have a current source GMV pi, and R0 will be presence of, it shows the presence of Early effect, and RC. So this is the small signal equivalent. When we consider the input side, when we measure the input side, this input Rin is equal to, so R pi in parallel with R1 parallel R2, which is the input impedance. Similarly, when I look at the output side, this is R0, this is Ri. So Ri is, we have R0 in parallel with Rc. So the output impedance, this is your output impedance. And this the gain is nothing but, when you write V0 equation, it is Gm into V pi. So this current is going to flow in this path. So this is plus and this is minus. So Gm into V pi, R0 parallel Rc. So what is V pi here? V pi is voltage here. So V pi is written as, you can consider this Rs, and the whole combination of this is nothing but Ri plus Rs into Vs. So this is nothing but voltage divider rule. You can use that. So you will get V0 minus Gm R0 parallel Rc Rin plus Rs into Vs. So voltage gain is nothing but V0 by Vs. So that is how you get this result. Right? We can make approximation. So this Rs is much smaller. So this whole term will become equal to 1. And if R0 is parallel to Rc, this R0 will be larger quantity and Rc will be smaller quantity. If you find the equivalent, it will be lesser than the smaller value, which is nothing but Rc, which is Gm into Rc. So if you make approximation, the approximate gain is minus Gm into Rc it is what considered. Circuit with emitter resistance, we consider this Re resistance and we draw the equivalent, and we have this Re present between emitter and ground. That is what is the difference between the previous circuit and this circuit. If you consider the presence of Re is when temperature is increased, my collector current is going to increase. If my collector current is going to increase, my emitter current is also going to increase. If my emitter current increases, the voltage across Re is going to increase. If Re is going to increase, my VBE is going to decrease. If my VBE is going to decrease, my IB is going to decrease. If my IB decreases, my IC will decrease. So this introduction of Re is going to bring negative feedback. So it stabilizes Q point against changes, against temperature changes, right? As well as when transistor is being changed, beta will also change. This change is also arrested by presence of Re. So when you take the output voltage, it is V0 is equal to minus beta. This current is going to circulate in this path. This is plus and this is minus. So it is minus beta times Ib into Rc. This minus says phase inversion between input and output. That is what is the meaning. If you give the input like this, the output will be phase inverted. There will be out of phase. That is the meaning of this minus. And as usual, we will find all these things. Vin is nothing but Ri. So this is Ri. So Ri is what? Ri is this R1 parallel R2 in parallel with this R pi into 1 plus beta into Re. So this 1 plus beta, the meaning of 1 plus beta is the base and emitter is going to differ by a current ratio of 1 plus beta. So that will come into picture, and this is called resistance inversion rule. Resistance inversion rule. If I do this arithmetic, you will get minus beta into Rc divided by R pi plus beta plus 1 into Re into Ri over Ri plus Rs. This if you make approximation, this Rs will become much smaller. So the whole term will become equal to 1, and you will have minus beta Rc R pi beta plus 1 into Re. So this R pi tend to be much smaller, and this if you write it, it is minus beta into Rc divided by beta Re plus Re. So again this Re tend to be much smaller, so it is approximately equal to Rc over Re. So this gain is approximate gain, and this is your exact gain of this amplifier. And if you consider R0, when you look at the circuit at the output side, it is equal to Rc. When I look at the input side, it is Rin. So R1 parallel R2, and you have what is called as R pi. Base and emitter is going to differ by a current ratio of 1 plus beta times. So it is into Re. So this is your input impedance. So this is what is the gain, input impedance and output impedance of common emitter amplifier with emitter resistor. When you consider this configuration, when you do the AC analysis, this capacitor is considered as short circuit. So the AC gain is decided by RC by RE1. So here you don't have any effect of RE2 on the AC gain. So gain is improved when you put bypass capacitor. When you consider DC analysis, this RE1 and RE2 is going to stabilize my Q point. So the contribution of RE1 and RE2 will be present in the case of DC. When you consider AC analysis, this presence of this bypass capacitor is improves the gain. So when without this CE, the gain is minus, approximate gain is RE1 plus RE2. So without bypass cap C, but with C, the gain has been improved because RE2 doesn't appear at the output equation. So this is what is the importance of putting bypass capacitor. And next, advanced common emitter amplifier. What is the advanced? Advanced in the sense, in integrated circuits, we don't have much space for fabricating resistors, so we need to replace this resistor by a transistor. So what we do is we put a PNP transistor and we take the resistance of this transistor to be RC when it is biased with properly biased. The properly biased in the sense we should bias in this region so that it is the resistance of the transistor is RC. When we draw the small signal equivalent, the gain is AV is minus GM into R0 parallel RC. This is what is the gain, and R in is this, which is nothing but RB in parallel with R pi. And when we draw or when we get the output resistance, R0 is, we have R0 in parallel with RC. This is what is the advanced amplifier concept, where we are going to replace a resistor by using transistor. By properly biasing the transistor in we are going to simulate resistor. Why? Because inside integrated circuits we don't have much space, and we have to spend a lot of money for fabricating the passive devices inside the integrated circuits. Fabrication in the sense the number of steps involved in fabricating resistors or making a resistor inside the IC chip is more. If it is more, then the cost of the chip will be higher. So that is what is the importance when you go into integrated circuits. We replace all the passive devices by active devices. And thank you all.